Today we're going to begin with the webinar on transforming multiphysics simulations through quantum computing, organized by ISCFD, the International Society for Computational Fluid Dynamics. And first of all, I would like to thank our attendees from any part of the world who once again are watching and following us on our events. And also, I would like to thank the members of BosonQ Psi who are joining us from India and the US for such initiative and in spreading the knowledge of quantum computing within the framework of multiphysics simulations. On behalf of the ICFD members and myself, we think this topic is of interest for the simulation experts and enthusiasts, since it is a shared passion and message, the spread of knowledge and about simulations, and especially from our side, CFD simulations. BosonQ Psi is an organization setting out a mission to reap the benefits expected from quantum computing and forever change the multiphysics simulations market. The stem of this institution is formed by Mr. Abhishek Chopra, founder, CEO of the company, and also pursuing a PhD at Rensselaer Polytechnic Institute in the US. Mr. Rut Lineswala, who is the co-founder and CTO, currently also pursuing a PhD in CFD for hypersonic applications at University of Minnesota, based in the US. And last but not least, Dr. Arish Pitchai, the company's advisor on quantum computing. Today, we want to present you the webinar given by BosonQ Psi, which we have recently established a partnership with them, but more on that later. Before starting this presentation, now I would like to inform you that the presentation will take about roughly 45 minutes and it will be followed by a Q&A session. Therefore, I encourage you to ask as many questions as you want on the chat, and these will be asked the speakers on your behalf. Furthermore, this webinar will be recorded and later uploaded on our YouTube channel. Without further ado, I will leave you with the members of BosonQ Psi and their presentation on transforming multiphysics simulations through quantum computing. Thank you.
Can everybody see my screen?
Yeah.
Okay. So thank you, Lord Jesus, and thank you, the team of ISCFD, Jamie, Joseph. Thank you all for giving this opportunity to speak at this platform. I was always on the other side and enjoyed so many great talks given by the people who come here. So it's a privilege to be here and to be able to give some new insight on multiphysics simulation done by BosonQ Psi. I'm joined with my teammates, team members, Rut Lineswala, and Dr. Arish Pitchai, who's a quantum advisor. So moving on with the presentation, for today's agenda, I just want to highlight that first we will be introducing the speakers as well as briefly about the core team. And then we are going to tell about the need for quantum computing, both from architectural limitation as well as from engineering limitation perspective. And then we are going to give an introduction to quantum computing of what actually this whole disruptive game-changing technology is. And then at last but not the least, what is BosonQ Psi doing? And why is it interesting to the community itself, both quantum as well multiphysics simulation community. So just to briefly introduce everybody, hi, myself Abhishek Chopra, I'm the founder and the CEO. And I'm currently pursuing PhD at RPI in US, where I'm specializing in developing high fidelity computational fluid dynamics code for rotorcraft applications. So mainly I deal with for something like electric VTOLs, helicopters, and all those regime, like low Reynolds number regime, and this whole PhD experience has transformed me because I've started as an enthusiast in CFD right from my high school, which I was very passionate about. But then slowly I gain more experience, and then went into like at start of my PhD went into high performance computing, where I actually saw this whole field that we talk about, doing LES and DNS simulations and different things. And then there was this problem that I will briefly talk about, what led me to founding the BosonQ Psi. And I finished my bachelor's, and I was very fortunate to attend Rutgers University, where I finished my bachelor's in aerospace engineering. And that's where I met Ruth and Hassan, who are other co-founders. So I will now let Ruth and Dr. Pitchai give a brief introduction about themselves and then move further along.
Thank you, Abhishek. Thank you, ISCFD, for allowing us to come here and give us a talk. Hello, everybody. I'm Rut Lineswala. I'm currently a PhD student at University of Minnesota, and our group, my group at University of Minnesota, what we do is we're looking at CFD of hypersonics. So we're looking at re-entry of vehicles in various different environments, so like Mars and other planets, as well as obviously Earth. But specifically what I do is on the FTSI, or fluid thermal structure interaction. So actually, so currently what I'm doing in my PhD is somewhat of a multiphysics simulation, which is nothing but a combination of several different multidisciplinary simulations. So I'm looking at, I would say it's somewhat of a new field, still is a novel field in the hypersonics, the fluid structure interaction, but because of the the harsh environment when we deal with in hypersonic flows, the thermal component is inherently kind of connected with fluid as well as the structure analysis. So yeah, so I'm looking at various different aircrafts that or not even aircraft, very different geometries, and seeing like, you know, the airflow around it. But not only that, given if we have, let's say, compliant surfaces along the different geometries, how they react, and not only how they react, but how they disturb the flow. So what will the new flow field be looking like? So it's kind of like a reoccurring or I would almost say like a cyclic kind of simulation. So a little bit about myself. Like Abhishek mentioned, I also did my Bachelor of Science in Rutgers University here in the States, and that's where I met Hassan and Abhishek. And in undergraduate, all three of us have worked on many projects. Like Abhi mentioned, we one of the projects that we did was on, yeah, well, it was a novel idea on the vertical takeoff and landing VTOL project. Another one that Hassan and I were part of were the solar car. And what I saw, like, you know, after learning what fluid was, and especially computational fluids, I just naturally just gravitated towards the field. And ever since getting exposed to CFD, I just become incredibly passionate towards it. And for all these projects, I essentially made up the ranks to become the CFD expert or analysis, or essentially became the aerodynamics lead for all of these, because I didn't want anything more than that, because I know, like, exactly what I want in my life, and it has everything to do with CFD. Okay, yeah, Dr. Pichai.
Thank you, Ruth. Good evening, all. Thank you, ISCFD, for this opportunity, and thank you, BosonQ Psi team, for giving me this opportunity. I'm Arish Pitchai. I pursued my PhD in quantum computing. That's when I got myself inclined towards quantum computing. I was able to foresee that the future is going to be quantum computers, replacing our supercomputers. So I started working on different algorithms and inventing new algorithms on how to solve computationally complex problems. And I had an industry experience in an MNC as an R&D quantum R&D engineer. And I'm currently working in Christ University, teaching quantum computing and data science to students in India. Thank you.
Thank you, Dr. Pitchai. Thank you, Ruth, for this wonderful introduction. So just quickly to introduce everyone in the team, we have Hassan, who's also our co-founder as well as the chief operational officer, and he has background in, again, bachelor's in aerospace engineering and is in biomedical field right now, doing some interesting stuff with data science. Then we have Josh, who's also a co-founder as well as chief financial officer, and he's also like he graduated from the same university which Dr. Pitchai is part of, which is Christ University. And then we have two wonderful people in our marketing team, Rajat sir and Shreya Jaswal. They take like all the posters and all the posts that you see in our social media and everywhere is put up by them. So we have a very good technical team as well, which I unfortunately was not able to put in the slide, which are working on the backside of things, which quantum algorithms as well as specializing in multiphysics simulation. So we have that good 10, 11 people team who are doing wonderful things, and hopefully to the people who are following closely BosonQ Psi, we will be able to show some promising results of like quantum computing. But to get to that part, we want to introduce in today's presentation the motivation behind why we are doing what we are doing. So to start with a brief history of what computers were and what challenge it faces now and in the future. So our first supercomputer, as most of you will know, that was the first generation computer that came out in 1946 and 59. And I think so these were in our middle school textbooks that they said that, oh, they're size of a room, and they were actually size of a room, like 30 by 50 feet of room size. Um, the interesting part was they were made of these vacuum tubes, which were like very large in numbers. And these vacuum tubes are very important. There were other components as like resistors and capacitors. And the need for computer at that point of time was to basically do something which is much more faster than a normal calculator. So that's why these computers were put together. And it was found that about like it can add like 5,000 numbers in like 1 second, and people like, wow, there is something much faster than calculator. So now then the things started to change from the first generation. The second generation of computers came in, and they were made of like transistors, and people thought that, oh, this is great now because the size is reducing. Then the third generation became the computers became much more smaller. It came into like ICs, and now what we have is the fourth generation, which are known as like the microprocessor, which are basically chips with like ICs integrated in them now. So this whole change was followed by a trend in computer science industry or computer industry, computer technology, you can say, which was basically that Moore, who was actually the founder of Intel, and he postulated that every 2 years, the transistors or the power will like basically the number of transistors will double in a processor. And actually that trend was very nicely being followed. And we could see that the trend kind of like moving away from what it was initially said in last like few years. This trend is actually moving away, and that's where the problem is. But to go taking a step back from that, there was there was a need that we need to increase the number of transistors so that we can basically do much more with the computer. So as I initially said, that the computer initially were made for doing like calculation, but then it came to doing more, and that's where the field of this whole multiphysics simulations uh, actually originated. So then there was a demand from these computers, and to fulfill that demand, there were two ways. Either we can decrease the size of these transistors so that it can be accommodated, like more can be accommodated, or we can do like layering. That's what you know as like multiprocessors now. So both of them were like both these techniques were followed, and as you can see in the picture, uh, both the size decreased and the layering was provided so that more number of transistors could be fit. But now what happened is that now trend if we keep on going with this trend of decreasing the size, because you can basically add a finite number of layers, so the only way to go forward is to decrease the size. And the size of these transistors have decreased to atomic level. And in July 2020, it was actually shown by researchers in Hebrew University of Jerusalem that one transistor is actually equivalent to the size of a single atom, which is like 2 nanometer. So that's very interesting. So going to the future of efficiency, what we initially had was this Intel 4004 chip, which was basically like which had about 2250 transistors. And following this Moore's law, and this whole thing that I showed in the previous slide about layering as well as decreasing the size, we came from something as Intel chip, which were basically of size 10 to power minus 6 meter, which is like micrometer, you can say 10 micrometers. And giving the power of like 740 kilohertz, we came into something as AMD, what produced last year, which is like, there are much more powerful chips than that. But the reason we put this into the slide is because it became famous because of the number of transistors it had. So you can compare from the left hand side to the right hand side the number of transistors that a chip in the modern era carries. And not only this, the size of the chip actually reduced from 10 to power minus 6 to 10 to power minus 9. So that's why we have 1,000 like 1,000 times much smaller chips now, or transistors, I would say. But the fast it got to like the range it provides, or the efficiency it provides, from 740 kilohertz to 3.4 gigahertz is immense. That's why we are able to have these supercomputers which can do AI, ML, like drug discovery in this time of COVID. Like, so many other things are possible because we have that kind of power. So all thanks to computer science. But now there is one thing, that performance is inversely proportional to the size. So the smaller the size is, the better the performance is. Because the shorter the distance between each transistor is, the faster will be travel of the communication. Now, yes, we can make things smaller and smaller, but every good thing has to come to its end. And that's what we are seeing with Moore's law and all these first kind of like I would say this whole classical computing itself. Because the major drawback is, from an architecture point of view, this drawback is the energy dissipation, meaning that if you pack so many transistors so close, the kind of heat it generates is immense, and it is not good for the circuit itself. So now the next attempt to reduce the sizes to, as pointed out in the last slide, last slide, that it is going to the atomic level, which is great. But now the problem is, we don't know actually how these atomic level like things work, because it is now you are taking everything away from Newtonian physics to something as like modern physics. And that's where um, this issue lies, that computers cannot become smaller anymore. Because atoms follow now, like if we make it more smaller, atoms will follow quantum mechanics rule instead of classical mechanics. Yes, in last 30 years we saw like 35,000 times increase in the speed, but what the future holds, um, we cannot say, because the Moore's law is, as I said, is dying soon. And that's why we, according to that law, we are able to only see that in next 30 years, we only will go like 50 times increase in the speed up than present, which is not very good. Because as many people in the call who are like from background in multiphysics simulations and everything, they are relying on these big machines to come so that they can process like large data and do these complex interactions that are happening between different fields, as well as like simply to put like to do DNS of a full aircraft, you need these kind of like supercomputers there. And that's where we need the paradigm shift. That's one of the things that from an architecture point of view, this is something that has been strongly said, that we need something else. And taking another perspective, which is the engineering limitation, which I think so will the most of the people joining in the call are very familiar with, is CFD. So just to take an example here to describe this limitation, what you see in the image is basically a tail of an aircraft. This was a simulation that was performed using the LES code of FASTA, which is the current code that I use in my PhD. This code was basically, this simulation was used um, to to show this the like when you put these um, these devices at the end of in the rear of your tail, what happens, and this was studied through like LES, as I mentioned. So LES is very expensive and time consuming. Now, one thing was there that we, and in academia, we enjoy this freedom of like not worrying about the cost and all, but there's definitely computational cost involved in it. And we have to be very selective of what cases we take to actually do these simulations. So for this simulation, we used actually 3 million parallel processors, and thanks to Argonne National Labs Mira supercomputer, which was one of the top supercomputers at that time when the simulation was performed, um, we still like took about 5 to 6 months to get the image that you actually see. So it involves the initial transient going away, and then it involves like those whole computational and then post processing. So that is a very long time. 5 to 6 months, even in academia terms, is somewhat like too long. And this is, I'm just talking about one part of an aircraft here. And I think so. Dr. Neil Ashton, who came in last of the talk presented by ISCFD, he pointed out this same issue as well, that in industry things are different. You actually care about the cost then, and with LES and DNS, which industry really needs that kind of accuracy, it's really not possible. So the line that I've said here, full aircraft simulation is not possible. I'm not talking in terms of like physics, it's not possible. It is just not possible because of the computational resources that it will need. And this, if and experts in the field of CFD, actually, Dr. Jamison and his group published a paper in AIAA conference. I think so it was 2018, where they mentioned that like how much computational power you need. So taking from there, if you go into the current trend of supercomputers, it will actually take like like full aircraft LES about 2050, and DNS about 2070 to actually make it possible in like feasible from like computational cost perspective. So there is another problem. Okay, we are talking, okay, we will wait till 2050 for these supercomputers to grow, but there is another challenge, which is the electricity limit, which is actually tied to the like the architecture limitation problem, is that the electricity requirement of these supercomputers are immense. Like um, if you talk about 2050, then you definitely are talking about zeta scale supercomputers. Um, and zeta scale supercomputers require about, like the prediction says, about 80 megawatt of energy, which is actually 4 times the daily need of San Francisco city. So that's like immense. And that's where we feel that we need some paradigm shift. And this paradigm shift is quantum computing. The world has known it. The computer science people have known it. And it's a very, very disruptive field, not only in terms of what it can do, but also that we actually need it. And that need has brought in this thing. But one thing that we have seen, and Ruth is, I know, going to touch upon that, is currently quantum computing is being applied in the field of AI, ML, but we are not seeing something in high performance computing applications, for example, multiphysics, because multiphysics is the driver for high performance computing until this point. Like AI, ML recently came, I would say, like last 4 or 5 years. But then we have to have these quantum computers being placed on the field that we really require, which is like multiphysics simulations. So I know I've talked a lot about, like, said, okay, we need quantum computing, but to give you a brief background of what quantum computing is actually, so I will now let Dr. Pitchai take over the presentation from here on.
Thank you, Abhishek. Do I have the control? Yeah. So I would like to start from where Abhishek left it. Well, just give an introduction of what quantum computing is, since the audience is a diverse audience. So I would like to give introduction to quantum computing, assuming that none of you are familiar with quantum computing. So it will be like a very layman term introduction to you all. Okay, let me start with what happened earlier in physics. Earlier in physics, people were thinking that light is a wave, light that travels like a wave that has amplitude, frequency, and all those things. But after few scientist experiments, like Young's double slit experiment and all, people found out that light is not only a wave, light also behaves like a particle. So light, when we reduce the intensity, it starts behaving like a particle. But so is it a wave or a particle? That was the confusion people were having, and they came to a conclusion that it has dual property. Light behaves like wave as well as particle. Most of you might know about this Young's double slit experiment, where Professor Young started shooting electron gun, and when he reduced the intensity, the electron started behaving like particles, like balls being thrown on walls. But when the intensity was very high, the light was showing interference. It was like behaving like wave, like how you throw a water in front of a wall, or if you have multiple waves, how do they interfere? So he was observing both the properties. So it started becoming so counterintuitive. So people started to get into the counterintuitive world of light. Not only light, all the subatomic particles like molecules, atoms, protons, nucleus, everything started behaving like dual in nature. So the two main counterintuitive nature of subatomic world is quantum superposition and quantum entanglement. I'll break down these terms to an easy description. Quantum superposition means if someone asks, where are you? You will say, if you're a student, you will say either you will be sitting in a classroom or you will be sitting in your, sleeping in your hostel. But quantum has a term called superposition, where you are capable of sitting at both the places. At the same time, you can sit in college as well as in your hostel. That is called quantum superposition. Not, I cannot do that and you cannot do that, but subatomic particles can do that. Like an electron or a proton or an atom can exist at the same time in multiple places. And the second counterintuitive property of a quantum particle is quantum entanglement. If you like, quantum entanglement is like actually it sounds like so fictional when you create a friendship between two particles, or when you entangle two particles, and if you make a change in one particle, the change will be reflected in other. Like if there are two friends, like one of them skips the college, it is obvious that the other might also be absent on the same day. This is called quantum entanglement. This happens in um, subatomic particles, and it was theoretically proved. Scientists took two particles, created entanglement. They kept one particle and in the country and the other in a distant island. They tested it in Africa and China, and it worked. It was practically proven. So there is a question in the chat room. I'll answer the questions at the end. So we are going to harness these two capacities, or these two properties, counterintuitive properties of electrons or subatomic particles, to make computation so efficient. Let me show how we can harness the superposition first. If I have to solve a function, or if I have to solve a simple equation, I have to take, let's say there is a function like x plus 3 equal to 0. If I want to solve this, I will say that x equal to minus 3 is the solution. Let's say there is a question like I have been given like 10 numbers, and someone gives me a complex equation and asks me to find which of these 10 numbers is the solution of the equation. Then I will have to drop every number in the part of x, and I will have to check which of the 10 numbers solves the equation. So classical computer takes n steps, but quantum computer is capable of solving that in one single step. A famous quantum algorithm called Dash algorithm is the proof for that. And it is also easy to store a lot of information in very small size. Like if I have to store 1,000 information, I need only 10 boxes of quantum bits. Quantum bits are otherwise called qubits. So if I have 10 boxes of quantum nature, I can store 1,000 information in it. That is 2 power n, 1,024 information in it. That was not possible in your normal classical computers. Next, if we have to harness entanglement, we have multiple applications of harnessing entanglement. One good example is super dense coding. Let's assume that there are two people, Alice and Bob, which is a famous example in all quantum books. That's why I took the same Alice and Bob example. Bob wants to encrypt a message and send it to Alice. So Bob has a list of gates, quantum gates, these I, X, Z and XZ or quantum gates. He should make use of, there is a special algorithm which does this, make use of this gate. What Bob should do first is he should entangle two particles. He should have one particle in his hand, and he should send the another particle to Alice. Then he should apply one of these gates based on the information, and he should send his particle to Alice. So whatever information is there in Bob's electron can be read only if you have the entangled other particle. Otherwise, you won't be able to read what is being sent by Bob. So this super dense coding is called like this is an alternative for classical cryptography where you can easily get breached. So this is a very good example for harnessing our entanglement. And superposition and entanglements are two very good tools or weapons which we are going to use to conquer the complexity. So I'll just, before explaining, I don't think explaining this in detail will be of like we don't have much time to explain these things. So I'll just give a basic overview of how do you look at a quantum computer? How can you imagine a quantum computer to be? Okay, first let me show you a basic atom. Like most of you know this. This is the Bose model. An atom has electrons revolving around the nucleus, and nucleus has a proton. So a quantum computer can have any subatomic particle as its building block. You can have either an atom as a building block, or you can have an electron as your building block, or anything. You can have a photon. So now I'll take an example of an atom. So let me first show you how classical computer works. When the computer is when you have something called registers in classical computers. When there is no power inside the register, it means that you are storing a 0 there. When there is a power, that is 5 volt or 12 volt of potential differences there in the classical register, then you call it as 1. So your computer works by storing zeros and ones, which everyone knows. Any character or any letter or any symbol is represented as zeros and one binaries in your classical computer, and that happens when there is a potential difference, it is 1. When there is no potential difference, it is 0. That is how a classical computer works. And you have gates which will flip the zeros and ones. One good example is a NOT gate, which flips 0 to 1 and 1 to 0, and you have many more gates like AND gate, OR gate, XOR gate, etc. But in the case of your quantum computer, one good example of same classical counterpart is ground state and excited state of atoms. You can represent ground state of an atom where the electron is closer to the nucleus, the first orbit, as your 0, and the excited state where your electron is in the next orbit as 1. You can also denote this off state and on state in matrix also. You have two states, so you should it's good to represent the state as a 2-column row matrix. So the off state has a 1, which means I'm storing a 0. If the on state has a 1, it means I'm storing a 1. So this is a very simple way of representing a quantum bit or qubit. How do I implement a gate here now? I knew a way to store the number, but I have to know a way to now implement a gate. Now in this case, I can call energy as a NOT gate. When I give energy, the ground state becomes an excited state. When I remove the energy, it moves from the excited state to ground state back. And that quantum gate is represented as a matrix. So we use matrices for representing all the states. We use matrices for representing gates. We use matrices for doing any operation in a quantum computing. Most of the time, we will be working with matrices. Not only NOT gate, we have many different gates which does the job of classical computing and which outperforms classical computing also. I'll just give an example of a famous gate called XOR gate or SOR gate. Many of you might know this, but I will show how it works. It's like a two-way switch. When both the switch are off, light will not be on, light will be off. When I switch on both the switches, light will not burn. There'll be darkness. If either one of the switch is on and the other is off, then I can see light in the bulb. This is how an XOR gate works in classical computer. We have a similar, we have a rival or a counterpart of XOR gate in quantum computing, which we call it as C0 gate. What happens here in C0 gate is we have something called a control bit. What control bit does is when the target qubit is 0, let me take you to the truth table. I have something called target qubit. I'm going to control this target qubit. When my control qubit is 0, I will not disturb the target qubit. I'll simply send the same symbol outside. When the control qubit is 1, I will flip the target qubit. Can you see the truth table? Now it is very similar to your XOR gate. But the thing is, I can easily reverse this gate. See, I'll take you to the classical gate again. If I say that, forget this A and B, don't look at this A and B. If I say that the output is 0, can you tell me what is the input? The input can be 0, 0 or 1, 1. But in the case of quantum computer, there are two outputs. If I say the output is 0 and 0, control qubit is 0 and the target qubit is 0, then you can easily say that the input of the target qubit is 0. If I look at this control qubit I'm getting 1 here and the output of the target qubit is 0, then I can easily find the input of the target qubit. the gates are reversible, which means I can save energy, and the reversible gates helps us to do more operations easily. And again, the matrix representation of the C naught gate is here. You can make a note of it and you can try it yourself how it works. Now this is how the building blocks of a quantum computer looks like. Now let me take you to algorithm part of quantum computing. Like, why do people say that quantum computers are so efficient? Everything started in the year 1994. The boom started in the year 1994 when a mathematician called Peter Shor invented an algorithm called Peter Shor's algorithm, which was capable of breaking or in other words, which was capable of doing integer factorization easily. Integer factorization means if I have a number integer 48, breaking that 48 into 2 cross 2 cross 2 cross 3. These are all prime values, prime factors. Breaking these into prime factors was a challenging task for a normal computer. Like if it is 48, it is easy. But what if the number is 100-digit number? So it was impossible for classical computer, normal computer to find the prime factors of 100-digit number. But Peter Shor's algorithm showed that it was easy for a quantum computer to do it faster. And we have a lot of platforms like Qiskit and OpenQuasm to test the correctness of the algorithms. And then came a new algorithm called Groover search algorithm, which uses again the superposition to help us search things faster. If you have let's assume that you have a phone book with numbers and then names, which was sorted based on the phone numbers and not with the names, then if I have to search Abhishek's number, I will have to go through all the let's say there are 1,000 names. I will have to search all the 1,000 numbers. But a Groover search, which is a quantum search, does this in much more faster than a normal computer. If normal computer does that in 100 seconds, Groover search does that in 10 seconds. That is the beauty of Groover search. Then we had a lot of very famous algorithm. This is the working of Groover search. I thought of explaining it, but since we are running short of time, I'll skip this part. We had Deutsch-Jozsa algorithm, Bernstein, Vazirani, and quantum artificial intelligence algorithms, and many more algorithms, which were changing the world of complex computations. And in the year 1998, we were able to achieve only 2-qubit computer. But in the year 2019, there is a company called D-Wave which makes quantum computers. They claim that they were able to approximately create a 5,000 qubit computer chip. There are many classical variants of quantum computers being produced by Rigetti, Google, Honeywell, Atos, and lots of quantum computer companies. And I hope we will be able to succeed in simulating CFD also using our quantum algorithms. Now I request Ruth to take over.
Yes, thank you, Dr. Pitchai, for giving everybody a little bit of a background of how quantum computing it works. Next slide. Okay, so now let's bring everything together. So why do we need so I hope the question of why do we need quantum computing for multiphysics is kind of answered, because we know that there are engineering limitations as well as architectural, like physical limitations on the computer science side. So that's why at BosonQ Psi, what we are doing is kind of integrating both of these technologies together. So in both, so in multiphysics, in quantum computing, sorry, multiphysics is a very niche area. And just to give everybody a little bit of background, multiphysics comprises of primarily these 6 fields, but it's not limited. Excuse me. It's not limited to these 6 fields. So we have heat transfer, structural mechanics, E&M, chemical reaction, acoustics, and obviously fluid mechanics. So talking more about fluid mechanics, we have the Holy Grail equation. I hope everybody, since I think everybody is in doing CFD, so our Holy Grail equation, Navier-Stokes equation. And for to solve the Navier-Stokes equation, our field of computational fluid dynamics is essentially created. And so on the right, you see the pyramid of the turbulence modeling. So at the bottom, we have RANS, LES, and then all the way at the top is the DNS. And as you can see, RANS is kind of the industry-wide accurate model where there's a lot of modeling, a lot of like, turning of the knobs and switches to kind of it is basically a ROM modeling or reduced auto modeling. So there is a lot of modeling that happens. Then when you go to LES, more of the physics dictates how the flow behaves rather than, and there is still modeling, but not as much as RANS. And then when you go ultimately to DNS, the direct numerical simulation, there is no modeling, and it's purely all based on real accurate solving in each cells, discretized cells per time step. So as you can imagine, DNS obviously takes much longer computational power as well as much more computation time to achieve that because you're solving it on each individual cells compared to, let's say, LES or even RANS, which is the lowest in terms of the computational cost, but as I mentioned, lowest in the accuracy. Next. So the motivation for this company is basically we want quantum computers that are much more use the technology of quantum computer, which is much more powerful than classical computers. So as Dr. Pitchai mentioned before, we want to harness the power of quantum computing, and so we want to use quantum computers to use to run these multiphysics simulation as Abhishek has previously mentioned on one of the examples. In that example, the CFD example of the vertical tail, we know how the complexities that go into it, and not only the complexity of the flow itself, but the how the flow behaves is incredibly complex, and in that the scientists were only able to do LES, which is not even the topmost in terms of the accuracy. So we want to design new quantum algorithms because, as Dr. Pichai have mentioned, there are a few algorithms that are out there. However, they're not. We don't have as many quantum algorithm as, let's say, people would like because it is still a new and emerging field. So there is not always going to be a counterpart in the quantum realm as we have in classical realm, which for years, I would say 70 years, people have been innovating on the algorithm side for the classical computers. So what we want to do is create a quantum algorithm that can actually speed up multiphysics simulation, and then once it speed ups, that also reduces the design times and the optimization studies. So like Abhishek mentioned, if you want to have for the vertical tail example, if you want to have these actuators kind of along the end of the vertical tail, you don't want to wait 6 months to realize, oh, okay, so in terms of efficiency, this provides let's say 1 or 2% of efficiency in terms of, let's say, the fuel in terms of the drag. Let's say we don't want to wait that long. So that's where quantum computing can really come into play. And as a software, what we want to do is we want to deploy a user-friendly application, a software that can be used without any prior knowledge of quantum computing, because at the end of the day, it is a multiphysics simulation. So we know our audience of our software is going to be primarily people like you guys, where we come from CFD, structure mechanics, or essentially any multiphysics simulation realm, where our knowledge of quantum computing might just end at, okay, like, there's the whole superposition principle, as well as, like, there's some little bit of the interference principle, but beyond that, we might not necessarily have the knowledge. So what we want to do is keep all that in the back end. So we, as a software, we want to like assign each qubit within the software itself, so that we want to give as much control to the users in the multiphysics realm, and kind of hide the quantum computing realm in the background, because that is not our main audience. Next. So our vision is to create the premier multiphysics simulation software for quantum computers. Now, I mean, I think everybody here knows about ANSYS. So ANSYS is right now the top-notch multiphysics simulation software. However, ANSYS is we all of us do know the limitations that ANSYS currently has, which is even though it's really good as an educational tool, why don't many let's say educational like academia researchers use ANSYS? Because of its lack of let's say parallelization with supercomputers, as well as the fidelity. ANSYS doesn't allow you to have as many like high fidelity models as we hope to do. Because as we mentioned, we know the power of quantum computing. So I mean, rightly so from ANSYS' point of view, there is no point of doing DNS if you don't have the computer power. Like, it doesn't make sense to even give you the option. However, because we're making a quantum computing software, the the computation power is not really a challenge for us, because uh, because right now classical computers are kind of stagnating for the Moore's law. Quantum computing is actually now starting to follow Moore's law, where, as Abhi mentioned, every couple of years we're gonna have double the amount of qubits. So our mission is to make a multiphysics simulation software, which is a main application for quantum computing as well. Because we currently have cryptography, AI, and AI, artificial intelligence or machine learning, that is primarily use of quantum computing is in these two realms. But multiphysics community has been kind of like leading the charge for the HPC, or the high performance computing community, because as you guys know, we use a lot of supercomputers. Like Abhi mentioned, for that example, they were using 3 million parallel processor at Mira at the I think ANL. So we, as a multiphysics simulation community, we are the ones leading the high performance community as well. So it only makes sense that the next step, or logical next step, would be to kind of move to the new technology that's kind of evolving from the computer science, which is quantum computing. So like I mentioned, we want to be the front runner of multiphysics simulation in the quantum computing, and develop our application simultaneously with quantum computing, because as we mentioned, that quantum computing is kind of evolving. Like, there's still a lot of breakthroughs that will happen, but quantum computing is like, we haven't achieved quantum supremacy in all of the realm, where quantum computers haven't necessarily beat out all the algorithms compared to classical. However, it has achieved quantum supremacy, as people call it, in some of the algorithms. So it has shown, like Dr. Pichai mentioned, quantum algorithms. Some of the quantum algorithms have already shown that okay, if the current supercomputers are unable to do, quantum computers have already been able to do it. So instead of waiting for quantum computers to develop and get it to its like final form, let's say, we want to develop along with it, and kind of have we want to push the quantum community and we want quantum community to push us to kind of, be at the similar stage. Excuse me. Sorry about that. And the last thing to talk about the multiphysics simulation community is the industry that we're dealing with. We obviously have the aerospace industry where we do a lot of CFD, structural dynamics, as well as, coupling of those two. And we also have the thermal portion. But not only aerospace, but kind of taking the broader view, we have the petroleum industry, renewable energy, which is a really hot field, especially I know in Europe, where there have been many countries are taking a lot of initiative for the renewable energy, especially like wind turbines. We also have the chemical manufacturing, where new, let's say, more efficient methods to kind of do, let's say, if you're talking about combustion, more efficient method to do the chemical reactions. And I know for in terms of hypersonic, that is a really like hot field as well, because when we're looking at hypersonic aircraft, because the aircrafts are moving incredibly fast, there's not enough time for the fuel to mix with air and then combust. Because most of the time what happens is, well, by the time they combust, they're essentially out of the engine. So there isn't like the combustion doesn't really help out the aircraft itself. We obviously have the automotive industry. Like again, Europe has many car companies, and I know like I'm a huge fan of Formula One. So there, in terms of the aerodynamics team, they spend lots and lots of time in the both in the simulation as well as wind tunnels, let's say. We also have the biotechnology. Like Abhi mentioned, Hassan currently works. One of our co-founder, he actually works for the biotech company who are doing like gene editing, developing technology, and for that they're using a lot of modeling and simulation. And obviously we have the astrophysics, which is essentially looking at like how stars explode and things along that line. And that's also, you're doing nothing more than like fluid simulation or even like particle physics, which is what we do at a hypersonic realm after after some point. But that's just a little bit of a short presentation about BosonQ Psi. And if you guys have any questions, let's go right into it. Thank you guys for listening.
Thank you, Ruth. Thank you, Dr. Pitchai, and thank you everyone for being patient. I know we might have gone a little bit ahead of time, but I hope we were able to present of what we are trying to do and what we are trying to achieve through BosonQ Psi, and we can and most of you, I'm hoping that got some motivation of like thinking about quantum computing and multiphysics simulation. So thank you, and I would ask ISCFD team to take over from here.
Thank you, Abhishek. Thank you, Rod. Thank you, Arish, for such an interesting presentation. Above all, on covering the basis of quantum computing and the different algorithms that we have available nowadays, and also for sharing your prospects in the future. It was quite interesting, the timeline that you gave for the LES and DNS simulations for a whole aircraft from as a CFD graduate in of a master's at Cranfield. I know how this can be, how much of a pain can be to wait for the supercomputer to finish the simulations. So on behalf of the ISCFD Society and myself, we thank you for the presentation, and also we will follow you closely, your success.